Okay, welcome to sections 1.5 and 3.5. 1.5 is about infinite limits and 3.5 is about limits at infinity. And hopefully through this discussion we can determine what the difference is because they do sound, quite similar. In our graphical analysis of limits, we've already seen both types of these limits. We've seen both an infinite limit and limit at infinity. Let's look at these two equations and the graphs below to understand it and just get a picture in our mind of what's going on. So I look at my f of x function here, and the first thing that grabs my eye is I have an open circle, so there's a discontinuity. We got a whole discontinuity at 2, and I also know that I've got this vertical asymptote at x equals 2. So down below in the table, let's just fill out this table. The limit as x approaches 2 from the left side. So that would mean I'm on this graph here as I head to 2 from the left. It appears that we're headed down to negative infinity. And if I come at it from 2 from the right, well, now I'm working on the right-hand side of my graph. Coming into 2, looks like I'm shooting up to positive infinity. These are what we call infinite limits. The limit results in infinity. So an infinite limit is a limit that results either in infinity or negative infinity. Contrast that with limits at infinity, and let's go analyze the f of x function one more time, but looking at it for something a little bit different. Also, when I was doing this problem, I noticed, or looked at this graph, that I had a horizontal asymptote here at y equals 2. How does that play in? Well, when I'm looking at my limit as x approaches infinity, so I'm letting my x value get super large to the right. So I'm looking way out here. Maybe there's my x that I want. I'm looking for infinity. Well, if I just track my graph, I can see how this function is going to settle in along my horizontal asymptote. So I would say here I have a horizontal asymptote at 2. My limit, when I look at infinity, the limit at infinity is 2. When I look at negative infinity, I'm going to be choosing an x value, so maybe on my x-axis, if I extend my x-axis, maybe I'm out in this range somewhere. What is happening to my graph? Well, it's going and coming up and reaching my horizontal asymptote from underneath, and it still has a limit that is 2. So notice this was the f of x function, so it deals with the graph of 1. A limit at infinity is a limit that occurs when x approaches infinity or x approaches negative infinity. So if you can get the difference down between the terminologies of these two, here we're approaching infinity, so this is called a limit at infinity, and I ended up with a horizontal asymptote. If you note, we had horizontal asymptote at x equals 2. Here, I had a vertical asymptote at when x approached 2. So a little bit difference. Look at g of x. Let's go analyze the g of x function. Well, g of x, a couple things that are popping into my mind. See if you can find the same things I notice. Vertical asymptote. And also we have a slant asymptote on this one. So this is a slant, isn't it? A slant asymptote. And then we've got this vertical asymptote. Let's see if we can pick up what's happening here. So as x approaches -1 from the left side, -1 from the left would imply that I am following my curve here and I'm coming into -1 from the left side. Well, that's going to head down to negative infinity. And if I approach -1 from the right side, I'm following this curve and it appears that I'm headed up to infinity. And thus I can conclude that I have a vertical asymptote at x equals -1. Conversely, let's look at when x is approaching infinity. So now we want to head clear out to the far reaches of the x-axis on the positive x-axis, and I can see that this is traveling upwards, and in my estimation, that's going to continue to travel upward as I head off my screen and reach infinity. And if I follow as I take out a very large negative quantity like, negative infinity, I too see that this graph is going to hit negative infinity. So now let's look at marrying a numerical and analytical approach to finding the limits. So not always do we have the graphic to just view and look at it, but we should be able to take a limit and break it down, or take a function and break it down algebraically. And one of the first things that, is a good try is to factor. And the reason I say factor is because if I put in 2 into this function, I get 0 on the bottom. So I'm going to try and factor and just get a glimpse of what's going on in a little more detail with this. So I know my bottom factors into x minus 2 and x plus 2. If I factor the top, I've got that lead coefficient that has to be a 2x times an x. And the only way to make 6, well, there's two choices, 1 times 6 or 2 times 3. I think if you play around, you're going to find 3 and 2 make it work. And when I analyze this, I notice that that cancels away. And that tells me right there that I've got a whole discontinuity at x equals negative 2. So I'd have a circle or an open spot in my graph. This particular factor tells me that I have a vertical asymptote. Can I prove that using limits? Well, I probably will be able to prove that using limits. If I come into 2 from the left, I've got 2x plus 3 and an x minus 2 is what the function simplified down to. And, if you wanted to try a number, maybe let's try 1.9. And here's my f of x, which is 2x plus 3 over x minus 2. If I plug it in, I'm going to have a positive number on the top divided by some very small negative on the bottom, and that's going to yield a negative amount. And if I divide by something super small, it's going to take me to negative infinity. And the limit on this is negative infinity. If I analyze this from 2 from the right, I've got the same factoring going on, right? This is the same problem as what we just did. So now let's analyze it 2 from the right. We know that this function simplifies down to this. So let's analyze now, maybe make a little xy chart. Here's my f of x function, 2x plus 3 over x minus 2. And you could choose a number like 2.1. Well, if I put 2.1, I'm still going to be positive on top, and I'm going to be slightly bigger than the subtracting 2, so I'm going to end up with a very small positive quantity. And if I take positive divided by a very small positive, I'm going to get infinity on that. And, that's going to tell me that I have an asymptote going on. On one side, it's headed to negative infinity. On the other side, when I come in from the right, I'm going to be headed to positive infinity. Take a moment and factor this problem. So go ahead and hit pause and factor it out. Okay, so I factored mine. The only thing I found factorable is the denominator, and you can see what I wrote down. Now I'm going to take and analyze that. So I really can't put negative 1 in here because I would get my 0 denominator, so I'm going to have to find other means to analyze this. So I'm going to go with the idea of approaching negative 1 from the right side and approaching negative 1 from the left side. So from the right side, I'm going to be slightly larger than negative 1. And when I put in negative 0.9, I can see where the top is going to turn out to be positive and the bottom is going to turn out to be positive as well, because negative 0.9 is not larger than 1, so I'll end up with a positive divided by positive, but this will be quite small on the bottom. And when I divide a positive divided by something super small, I'm going to get a positive infinity. Positive divided by positive gives us positive. Do the same analysis over on the right-hand side. Well, if I square out that negative, it's going to be positive. Add more positive to it, it's going to be, oh, and then put in negative into there, and that too is going to turn positive. So I can see how my top, if I add three positive numbers together, I'm going to get positive. On the bottom, if I have negative 1.1 going in there, that would be a negative value multiplied by 2. This will turn out to be super small, negative, because just pretend like, you know, you have even a smaller, or a number that's closer to negative 1 from the right, or from the left side. It's going to be a very, very small number in our denominator, and that will turn out to be negative infinity. And I think we can justify the fact that we're going to have a vertical asymptote at x equals negative 1. From the left and from the right, it's approaching infinity and negative infinity. All right, on the back side, it says graphically, an infinite limit will always yield a vertical asymptote. So just helpful to remember. In pre-calculus, we discovered through observations that such a graphical property existed when a factor in the equation would not cancel out of the denominator. So if I end up with one of those factors that I just can't cancel away, you learned last year that that is going to lead you to a vertical asymptote. From this point forward, it's not a viable justification for the existence just to say, well, it didn't cancel out. So you can't use that sort of logic to say that there's a vertical asymptote. We will come at it from a limit perspective. So our justification for the existence of a vertical asymptote using limits will, you know, have to take into consideration x as it approaches this value a from the right side. That's a plus sign, and that will either yield a positive infinity or perhaps a negative infinity. Not sure which one, right? And also, or let's say or we can have the limit as it approaches a from the left of the function equal a positive or a negative infinity. And with either one of those, we will end up with a vertical asymptote. Analyzing down below for the function below, find any vertical asymptote that exists and then justify your answer using limits. So let's go ahead and factor. Why don't you hit pause and factor it? Okay, I got my factoring done. Hopefully we agree on our factoring. And the first thing I noticed was that I had x plus 3 canceling x plus 3. And then I was left with this factor that didn't factor away. So immediately my prediction is that I have a whole discontinuity at x equals negative 3, and I have a vertical asymptote at x equals 1, where this would turn out to equal 0 if I put in 1, and this would turn out to equal 0 if I put in negative 3. So that's my prediction. Now if I justify using limits, I should be able to prove this by this existence idea of limits. So as I approach 1 from the left, I note that, so that's like putting in a 0.9, something a little bit smaller than 1, I'm sorry. And that's going to give me a positive number on top and a very small negative number on bottom, which will lead me to conclude that this is headed to negative infinity. And up here, it already said, if I head to infinity or negative infinity, I know I have a vertical asymptote. So, you know, I could say since the limit as x approaches 1 from the left of this function, which is h of x, change that to h, is equal to negative infinity. Since that's true, a vertical asymptote exists at x equals 1. And that would be enough justification right there. But let's see what's happening on the other side of 1. So I chose a number slightly larger than 1, so I'm coming into 1 from the right. If I do so, I'm going to have a positive over, well, if I put in 1.1, this is going to be very small and a positive, and that's going to yield a positive, that is infinity. And there we go. So we could make the same justification over here, since the limit as x approaches 1 from the right of h of x equals positive infinity, a vertical asymptote exists at x equals 1. So just a little bit more secure in showing from limit perspective that a limit, or that a vertical asymptote exists because we're going to infinity or negative infinity. Holds a little more credence than just saying, oh, you know what, it didn't cancel away, so I know I have a vertical asymptote at 1. Okay. Okay, sorry, I thought I hit pause, but I hadn't, so you have a little dead space in between there. The last thing here, let's just finish this video up. Let's develop analytical procedures that we can use to find limits at infinity. So what you'll notice on all of these 3 problems here is the fact that we're headed either to infinity or negative infinity. And basically a limit at infinity describes the end behavior of a function. So what's happening as I travel way far to the right on the x-axis, what is the behavior of my function doing? And we'll find different ways to analyze this. So let's see if we can find the limits here at infinity. One thing I remember from pre-calc is the fact that the largest degree really holds the power for the function, and the behavior is going to mimic what that largest degree does. This is a cubic function, as we all can tell, based on the 3rd degree there. And I know kind of a little bit about the behavior of a cubic function. You know, they're either like that or like that type of function. So, and they can even do that number if we wanted them to. So, if I put in infinity, I'm going to just pretend to substitute infinity in. So if I substitute a positive infinity, or think of a very large positive number, and I cube that very large positive number, it will remain very large positive. And then I multiply that by a -3, well, that's going to lead me to a negative infinity. So as I head to the right on the x-axis, I can be expecting that my function is going to be traveling, you know, way downwards, because I'm headed to negative infinity on that one. Next one, what degree is this function? Well, the first thing I notice is that I'm getting an x to the 2nd power times another x times another x. So it's kind of like I've got a -x times a -x times an x times an x, which would lead me to an x to the 4th. So this looks like a quartic function. And if I put negative infinity into this, I'm going to have negative infinity getting squared in the first one. And then I'm going to have times a negative infinity and times a negative infinity, because those x values are going to overpower, you know, anything subtracting 3 or adding 1 or adding 4. So very minute changes with those additions or subtractions. If I take a negative and square it, I'm going to have a positive large number. Here I'm going to have a negative large number and another negative large number. Well, negative times negative gives me positive. Large times large times large is going to lead to super large. So this has a limit at infinity. This one would have a limit at negative infinity. And finally, this last one, another thing we learned in pre-calc is if the numerator and the denominator have the same degree, then I look at the coefficients of them, right? And so this one is going to have a limit of -2. So top and bottom have the same degree, and therefore we will use the coefficient. Compare and use the coefficients to help us be informed of the limit. And so we get -2. That's enough for today. I know that's a long video. We'll finish up in class with some homework.